Hi, everybody. Happy Space Week. Rob here from MTU's Black Rock Castle Observatory. I'm joined by my colleague Frances, who you all will know very well as the Irish voice of space. You've seen her on RTE, News Talk, all sorts of platforms, and many of you will be familiar with her from teacher training sessions as well. We're also joined by a very special guest, Dr. Jan English, who is an astronomer and an expert in investigating galaxies, specializes in scientific visualizations, and is also a visual artist. You're very welcome, Jan.
Thank you.
And was at college with me. So Jayan
Yes.
and I know each other. We're not going to say how long, 1980s, but we were in college together in Toronto.
That's really cool. It's always great to have guests on our PCO
And
videos.
Canadian guests too.
A very special Canadian. I understand you received one of Canada's highest orders, Jan?
I saw
Yes, I
member of the Order of Canada.
yes, that's true. This is my whoops, other side, little pin. So do I have it on the right
You
side?
do, you've got your little pin.
Yes. Yes, that was very kind and surprising. Very surprising. It's for kind of integrating art, public outreach, and science together.
That's really cool. So what we're here talking about today, guys, is color in astronomy. And this is spurred on by a lot of you will remember back in May, there was a lot of extreme solar activity that led to the aurora borealis being viewed pretty much all around the world. It was wonderful. I
Thank
got
you.
lucky enough to see it.
Thank you, Rob, for sharing that where we were clouded out in Cork. I know
Yeah,
you saw it, Rob. You were
I didn't even
sharing
see it
the
with
most
intention.
amazing pictures.
Yeah, I literally went out to let the dog have her midnight rest break and was just looking up and happened to see this green purple kind of thing in the sky going, that doesn't look right. And I was like, oh, wow, that's the Aurora Borealis. So that was a
Was
bit
it
of luck.
really that color, Rob?
Oh, it was intense. Like I
Wow.
genuinely was surprised because something we're going to talk about in a moment is how sometimes we might need to intensify colors for the purpose of visualizations to
Yeah.
make things easier to understand. And I'd assumed every photo I'd ever seen of an aurora was, in some way enhanced or manipulated, but I was like, wow, no, I can really see green and purple. Now, I will add the caveat that I'm a little bit colorblind, so I perceive things a little bit differently to other people, so that may have had some impact on it. But it was very obviously not, a cloud or some other phenomenon in the sky. It was the first time that I looked up and went, that's definitely what that is. That's so cool.
Yeah, because I missed out on that one because we were cloudy here. If I'd realized just how amazing it was for everybody else in real time, I would have gotten the car and driven north. I think the cloud bank was just over the southern part. But I grew up in Ottawa. I've seen aurora before. I just, I've seen the kind of dull ones. I've seen the green. All right. So the most common aurora color is green. And auroras are, we say we're talking about color and astronomy. This is kind of sort of color and space. We're seeing the effects of the sun and the particles that stream off the sun, which are happening all the time. Occasionally they arrive at a gallop all together. And this is what happened in May, that there were multiple eruptions from the sun. We call them CMEs, coronal mass ejections. One of them kind of cleared the way, and the next one followed behind it and arrived. Whoop. And these energetic particles interact with the upper atmosphere and give us a glow. Depending on what they interact with, which is dependent on the height in the atmosphere and how fast they're going, you get these different colors. It's linked to how we see color in space because we do have atoms doing something, getting a little extra energy and then getting rid of that energy as light. So the same way in which we see a spectra of a star or a spectra of another extended object related to the energy of going on in the atoms, the ionization, all sorts of various different things, we get the colors. But green, it's mostly we're getting oxygen molecules. So oxygen molecules, 100 to 300 kilometers up, they glow and you've got your nice green. People who have done some chemistry may remember flame tests where you take a little dollop of something, stick it in the Bunsen flame and see what color you're getting. we're getting towards that kind of idea. So we can link this to the curriculum, to flame tests that you may have carried out. Now, Jayan, when you're living in Canada, do you see aurora?
Yeah, so we see aurora all the time. I found it really interesting in Manitoba, which is a very flat province. Indeed, we're kind of in a bowl of an ancient seabed. Um, when you look up for the aurora, it's like a dome of white over your head. It's hard to distinguish from a cloud, except by its motion, actually. And I didn't get to go out of town. I was too busy to take a drive out of town for that aurora. And again, like I've seen lots of aurora. So, but usually in Manitoba, I don't see the spectacular colors because I'm in the city. And I went up onto the roof of an apartment building with a friend, and we took a lot of photographs. And then we were watching like this white stuff kind of move around. You go, aha, that's not a cloud, that's aurora. And then we would set up our longer exposure times and get beautiful colors with terrific uh, parliament buildings behind it and in front or just in the
Yeah.
scene. Um, and sometimes I also want to make sure I say that our observations in the winter, we have a teaching telescope out at a darker site. And it often means that the students can't collect their astronomy data because of the aurora. It's so bright.
Not such a problem in Ireland where auroras are just less common. The magnetic North Pole has moved a little bit from where it was when I was growing up, when it was quite definitely in Canadian territory, but it's
Yeah.
still the other side of the North Pole from us here. So we're just less likely to get aurora just because of the magnetic north and where it's located. Whereas Canada gets the magnetic north that little bit closer. So the magnetic field lines, which affect the energetic particles, means auroras are more common in some parts of the world. Now, the one that everybody went crazy for on the 10th of May had the red. Sometimes there's blue. I understood, I had to look up why do you get blue? And sometimes you get blue if the aurora happens just after sunset. The top of the aurora is reflecting sunlight. So much like you get the noctilucent clouds, you're getting this beautiful blue, blue, blue color. And again, it's going to make your astronomy hard if you're looking through stuff that's, space adjacent, as in the top of our atmosphere.
I think you'll get over it if your night of astronomy is ruined by a spectacular aurora. You'll be like, okay, I'll just come back tomorrow night. Not the end of the world.
Yeah, and solar astronomers who study the sun, they're just delighted. All right. There's actually magnetic networks in Ireland measuring what the sun is doing, because besides making the beautiful aurora, it can have impacts on electricity generation, electricity lines. It can have an impact on how we carry out everyday life. If you've got all this charged particles zipping around the atmosphere, that's electric current that induces further electric currents, which can be a bit of an issue, a bit of a problem.
So I had mentioned how I had assumed that some of these images were enhanced either for astrophotography reasons or to help communicate the images. Jan, I noticed something that you were very familiar with. Can you maybe explain for people who aren't familiar why we might want to enhance images or exaggerate certain colors in an astro image?
So if you're looking at an image from, say, the Hubble Space Telescope, though this is applicable to radio telescopes as well, any telescope, um, we collect the data in black and white. And that's so we use all of the hardware to capture all of the photons that we can. So we have the particles of light. We want to have a light bucket that catches all of them and devote all of our instrumental energy to collecting these photons. So we don't encode color at all at the instrumental level. So we select different wavelengths, so different ranges of energy using filters or channels in a radio telescope. So you will pick something that's high energy, like the ultraviolet. You can pick something that's lower energy, like the infrared. This is what happens with the Hubble Space Telescope. So we have these black and white images aimed at the same target, but the images look totally different because they tell you about things like if it's ultraviolet and high energy, it's telling you about the young stars in a galaxy, say. And if it's in the infrared, it's telling you about the older stars in a galaxy. And they're in different positions in the galaxy. So by doing this, we can make a contrast between what's physically happening by having these two different black and white images. And we'll get a third black and white image, which will be covering all the colors we see from blue through orange, almost getting all the red, but not quite, a little bit of the red. So all of our colors are captured in just one image. And we have to decide what color we're going to assign that image. So it could be assigned turquoise, it could be assigned blue. All of those will be true to the actual science data. So now we have black and white images. And what we do is we assign colors to them that tell us about the science. So we are going to assign, in this example, a very common color assignment would be blue for the ultraviolet, red for the infrared, and then green for what you would see with your eye. And when you combine those together, you get in a galaxy, the young, old, and intermediate age stars. So there we're showing you the spatial distribution of those stars. And when we have the spatial distribution of those stars, that tells us something about how the galaxy formed and how it's evolving through time.
That's really cool. And I guess people are kind of familiar with how you would use color to communicate things through like graphics such as, climate change and like how the temperatures have changed over the years. We tend to assign red to heat, whereas blue is to cool. And I think in that context, people can really understand the value of correctly or of assigning a particular color to a particular phenomenon because it makes things easier to understand. But are there artistic elements that you need to keep in mind as well? Because I know, for instance, when I started learning to paint watercolors, that they recommended that you use cool colors to paint the background and warm colors to paint an object that you want to pop out. Is that something that you guys have to kind of keep in mind when creating an image that you don't accidentally highlight something that's not highlighted?
Absolutely. So, I mean, when people first started to assign colors in these images, they were just completely uh, cultural assignments. So you used cold blues for cold temperatures. That's very cultural. And it doesn't work with the eye-brain system. And what you described for your watercolors works with the eye-brain system. So what happens for blue is that color recedes and warm colors approach the viewer, right? So one of the things that I advocate for is using that eye-brain system perception for selecting what colors you're going to assign to objects. So when we're doing something like these young stars, and if that's the highlight, if that's the narrative of the scientific paper, then we have to use a warm blue. So those will pop forward. So, and use a dull red. So the older stars will recede. So I advocate all the time for using techniques from art and design to create your image if you're making a public outreach image, or if you're making images for your own colleagues and you want to communicate something at a glance, you want to support the eye-brain system so that it's more easily interpreted by your brain. You want to use this because they're cognitive tools and they help you think.
It's good that you're considering it and advocating for it because even something as simple as I mentioned, I'm colorblind. The number of presentations I've been to where somebody's after writing something in red on green backgrounds and I just can't read them. That's thankfully something people are becoming more and more aware of. But like, there's just so many ways that color and how we perceive it can affect our capacity to understand or just absorb information. And it's cool that you mentioned like the UV light. That's something that we can't really see ourselves, the UV spectrum. That you find a way to look at it and study it because that's something that's really, I think, that astronomers and physicists are particularly good at. And my background was actually in biology, and it was only in recent years I think that we've started to properly figure that we have our own biases. So, for instance, people would have spoken about, well, that flower is yellow, and that is obviously yellow to attract bees. But they were doing that using their human eyes to see what a yellow flower looks like. And when you look at it under UV light, it actually looks completely different. So the bee may be seeing something completely different. There may actually be patterns in what appears to be just a very simple yellow flower to us. So being able to assign a visual cue to something that we can't see so that we better understand the world is just such a cool concept.
Yeah. One of the things about doing something for people who are colorblind is we can't accommodate all of those things, all the different kinds of color blindness. So if you have a redundancy cue, like light through dark at the same time, if you're able to do that. So I'm going to back up 1 second. So I just talked about public outreach images. And for those ones, we're going to have a grayscale that is based on the data. This star is brighter than that star, right? That sort of thing. But let's say you're making a map of something, and a map is scientific visualization. And if you're making a graph, your graph is information visualization. So the color approaches apply to all of them. But if you're doing a scientific visualization where you're making a map of that flower and you don't have intensity information, brightness and darkness, you can assign brightness and darkness to it. So you have this other cue for someone who's colorblind. So say I put green and red together and they have the same value in terms of tone and grayscale. They're the same lightness. You won't be able to see the green and the red, right? But if I make them light and dark on a dark background, the light's going to pop forward, right? So someone who's colorblind can see that. So they can actually see what you've done as long as you do play with your grayscale tones along with your colors.
Really cool. And like what you mentioned about astronomers taking everything in black and white is kind of what we're familiar with here at the observatory because we have the large telescope on the roof that we call Big Bertha. So we only ever really see black and white images. I know she recently got a color camera for, I think, just astrophotography purposes for fun. But as Jan says, it is always black and white images we capture when we're doing research. And it kind of drives home something that like is kind of intrinsically true to humans is that even with the naked eye, we see things at night dark anyway because we have rods and cones in our eyes, and one is good for seeing color, the other is good for seeing black and white. The cone is picking up the color, whereas the rods are the what give you your night vision. So we tend to not see color at night anyway. But one thing that we do sometimes see, Francis, is a little flash of color in like a meteorite, for instance. So
Well,
how does that happen when it's like so dark out?
well, it's even interesting the color of stars. So I see the little hints of colors of well, the planets are quite easy. Mars comes out with a red tinge to it. Some of the stars we see in the night sky do have a different coloration. As Jan was saying, sometimes that's telling you about the age of a star, the young blue, the older red. Arcturus is fabulous. I mean, we're recording this now at the middle of the summer. Arcturus is there in the night sky with this real red tint to it. Not everybody can see that color as clearly as others. My husband is just no good at colors at night. He looks at these stars and he's going, "What do you mean it's red?" I'm like, "It's not a traffic light red. It's just a little reddish glow." And he's like, "Yeah, okay, maybe." So people's eyes are different in their ability to see color, but generally you need a certain amount of light to see color, to be able to get at that color recorded in your eyeball. The flashes of color that are the rare ones are with our shooting stars, and we're heading into August into peak shooting star season, although there's another great set of shooting stars that appear in November. And these meteors sometimes have a flash of color to them. Now, that is much like our auroras, sometimes dependent on where they are in the atmosphere. They're heating up the atmosphere. So these are space adjacent. It's stuff from space coming into our atmosphere. It's pushing the atmosphere, warming it up, and getting it to glow. So generally, if you have a fast meteor zipping through, the color you're going to see is related to the actual object, the small bit of space debris. A lot of meteors are slow, and they're going slow, then they're heating up the atmosphere and you're seeing the atmosphere color. So I've never seen a colored meteor. I've seen a handful of really bright shooting stars. There was a spectacular one about 4 or 5 years ago that everybody saw except me. I was going to an after the wedding event. I got there on time, and all the people who came in late going, "Did you see that? Amazing." No, I was on time inside. All right. But every
Great.
now and then you do get these amazing fireballs, and sometimes you'll get a persistent train. Oh, Jan, you're going to tell me that you've seen an amazing. Okay, tell me.
So
Tell me.
the Leonids in November,
Yeah.
I was at an observatory in Canada. We're very lucky to have this now classic or ancient, however you want to call it, radio telescope observatory in Penticton, British Columbia, called the Dominion Radio Astrophysical Observatory. And knowing that there was going to be a meteor shower, all these astronomers and their families took lawn chairs out to the observatory where it's nice and dark. And we lay on the lawn chairs and looked up, and they were green, oxygen, heated up atmosphere, streaks of green. And I was talking to someone, I was looking at her, and a meteor was behind me, unbeknownst to me, and her whole face was bathed in a green glow. It was like, I missed that meteorite, but
So
it was
cool.
such great to see her face all green.
Oh, I know. See, the Leonids early, mid-November, they are one of the best. They're fabulous. But of course, the Perseids get all the attention because they're in August. They're
Yeah.
the ones that everybody likes to go out and see in August. Geminids are known for having blue-green trails, which is linked to the nickel and magnesium that's in those bits of space debris. So, I mean, red, very, very unusual. Okay. If you've got calcium, one type of calcium will give you orange red, ionized calcium will give you violet. So, all of these colors are related to what's in the meteorite, depending on the speed and, of course, depending on the altitude and the whole lot. So, there's a lot of things going on to unpack about it, but they're all transient. They're quick, they're gone. They're of interest, they're attractive, but the amount of science you can get from them is limited enough because how are you going to observe them? We do have whole sky meteor cameras where we put them up, all right, and try to track what's in the sky. But again, you're back there to what are you recording? Black and white. Are you filtering? Are you doing your channel you're looking at? So you've got to decide what are you interested in? Are you looking for their intensity? Is that you're going to record that as the number of photons appearing? And then you've got to have your channels, your filters to be able to know the color of what you saw. You know, always a balance.
That's really cool how you can use color to determine what elements might be present in a meteorite. But I know that's something we can actually do with like gases out in space and even potentially the atmospheres of exoplanets through things like spectroscopy. So Jan, for somebody who isn't familiar with spectroscopy, could you maybe describe, how the process works?
Uh, sure. So if you think of a prism, it bends the white light that's coming in into different wavelength ranges, so different colors. And the, there's just kind of like a mnemonic to remember that violet bends violently. And so the red doesn't bend as much. So the colors spread out. And then you can use those colors, you can use them. So if you have white light and you spread it through all of these colors, you can count the number of photons in each color, each of the wavelengths, and that can give you the temperature of a star, for example. But if you have gas, you can do great things. You can have one ionized line. So you can have one line that emits because of the interactions either with the electron and the proton, or just the electron flipping over. It will create one wavelength of light. And that's an emission line. And using that line, you can use the Doppler shift. So you get like when you have an ambulance going by, if it's coming towards you, it's and then as it goes away, right? This happens for light too. So as it comes before you, towards you, it is high frequency, and high frequencies are short wavelengths. Those short wavelengths are bluer. And then those that are going away, they're lower frequency. So those are going to be more red. And that's how we get our red shift and our blue shift. So one of the things we can do with spectroscopy is we can use for example, in the optical telescope, we use things like tiny prisms or grates. So some glass with a lot of lines in it to make the light bend, and then we can count up those photons at each energy point in a spectrum. In radio telescopes, it's like flipping through the channels on an old radio receiver, right? So you're going to go like through different channels. The way cool thing about a radio telescope, and there's also optical instruments that now do this, is that you don't just get the intensity of like a dot, just you get a whole image going so you get a whole bunch of different images like and you've got a 3D cube. So you've got a spectrum, but you've got images, and that means you can look at how a galaxy is rotating using spectroscopy. So in the first image coming towards you, there might be just my hand. The next one's going to be my forearm, my elbow, right? So you get little bits of me rotating, right? Like this part's coming towards you, this one's going away. And so you can stack all of those images up and you can see the whole galaxy. But this whole change in frequency can be converted into velocity for the motion of the galaxy. And I can measure how much that galaxy is spinning, what its velocity is for its spinning. And once you have it spin, you can calculate how much dark matter is in the galaxy.
That's awesome.
Did I just go too far along here? Did I like go way from color? Anyway, so what happens then, these are all black and white images, and I can color them with a warm blue to come towards you, getting back to your art and your painting, Rob. And I can color it a dull red to go away when I put all these images together, and I can show you a map of how this galaxy is rotating. And for you, I will make the dull red dark and the warm blue light. So even if you don't see those colors well, you can see the galaxy rotation.
That's really, really cool.
It's very
so
cool.
That's working with like emission spectra rather than is it absorption spectra as the other type?
Yeah, the other type's absorption spectra. This type, the emission spectra, is generally easier to work with. Like you get ionized hydrogen in the optical telescopes, and you get it's just how the electron flips over in a hydrogen atom that causes one state of energy is higher than the other. It wants to be in the lower state of energy, so it flips over and emits a photon, releasing that extra energy. So though that's an incredibly common phenomenon in the universe, just because hydrogen is one of the most abundant regular element in the universe, and there's piles of it. Everything's built out of it. So that means that that's, in my mind, easier to deal with because our telescopes can detect these emission lines more easily, quicker, so more economically. So in an absorption spectrum, you sometimes have to sit on it for a long time until you get the dip if you have, I gave the example of the prism spectrum, right? Where you've got continuous light at photons at every wavelength. And then you have to wait until you have to take a lot of time to observe an object so that then you see the subtle dip in the wavelength. But you can use absorption spectra if you want to measure. This is actually another cool way. I hope it's not too much of a tangent, but it's another cool way of measuring dark matter in a galaxy. So what I just described was the gas in the disk of a galaxy, but not all galaxies are disk galaxies. Some are elliptical galaxies. They have hardly any gas in them at all. So what you do is you actually look at globs of stars called globular clusters out in the halo of these elliptical galaxies, and you look at their absorption spectrum to see where the absorption has shifted, blue shift and red shift. So you can do it that way too. Little more time consuming, or a lot more time consuming.
So
Oh,
we're
yeah.
developing a game at the moment called Terrestrial. It's a Science Foundation Ireland funded project, and part of what the game will involve is people figuring out what elements are present in an exoplanet's atmosphere based on an absorption spectra. So
Oh, okay.
um, to people who are playing the game, what they're going to see is something that looks a little bit like a rainbow with little black lines going through it.
Right.
So Jan, what you're saying is that the black lines are effectively where that little dip would be
Yeah.
in the absorption spectra.
Yeah.
Very
That's right.
cool.
And then what you can do is you can take uh, say it's called an arc lamp, but you can measure the spectrum of some chemical element you're interested in, let's say oxygen, right? And that gives you a fingerprint of those black lines. And then you can match those black lines up to the exoplanet spectrum and see, oh, does it have that fingerprint of black lines at particular wavelengths, particular energies? Does it have oxygen's fingerprint of black lines? And go, well, yeah, that planet has oxygen in it. That's kind of the search. We really want to find oxygen, right? So that's what you can do is you measure the fingerprint of the absorption lines on Earth and match them up to the exoplanet. The other thing you can do is you can look at the integrated light from a planet star system and watch the planet itself will absorb the block the light from the star when it's passing in front. So you can get the motion of the planet as it can move uh it can move it can shift because it's doing a blue shift and a red shift because it's doing an orbit, right? So the
I
light
just
can
think
shift.
that
You can find the mass of the planet this way. Yeah.
I think what's fabulous is you've gone from scales of galaxies and how they move, telling us about dark matter, and the same Doppler coming
Yes.
towards, going away, goes down to solar system level. I
Yes.
just think that's
Jesus.
remarkable. I can even remember at one point in college doing Doppler shift with Saturn's rings to know how Saturn is turning. Like you can,
Yeah.
the same powerful technique comes all the way up and down. It comes all the way through
Yes.
astronomy. Yeah, it's just very cool.
Yeah. There's great animations around for like transits and measuring transits of planets and
Mhm.
measuring the masses in the planetary systems to find out whether it's a Jupiter-sized planet or smaller planets and so
Yeah.
on. So
It's interesting. We've done a little bit of work on exoplanets, and it's one of the research interests at Blackrock Castle. Uh, I thought it was kind of interesting that the big Jupiters are predominantly found because they're easier to
yeah,
find. You know,
yeah,
there is a very much a bias. And sometimes in my bio, I say I'm old enough to remember when there were no exoplanets.
yeah.
Jan, was there a course in it when we were in college?
Yeah, there were no exoplanets.
No,
And then it was so
no, they
exciting
they
that
hadn't
there
been
were.
found.
And I think, I mean, at that time, it also shows the bias of the public, right? We thought any other solar system we found would be like ours, that ours would be a typical solar system.
Yeah.
Of course, the whole huge range, variety of planetary systems is astonishing. And it really makes you think like, yeah, there are no Mr. Spocks because there's no systems that are hardly any, we haven't really found systems that are twins or
No.
even siblings or cousins to us, right?
Yeah. Yeah.
So.
Well, I think one great way to wrap this up, guys, as this has been a fascinating conversation, is to touch back on something myself and Francis were discussing just before we hopped on the call, and that's how analogy can be such a useful way to communicate in science communication, because not everybody can understand the raw science. So finding ways to help people understand something through an experience that they're familiar with is a really, really valuable skill set for a science communicator. And Jen, I know you're very passionate about using art as a way to help communicate scientific concepts. Can you maybe speak a little bit about what makes art so useful in that regard?
I think I touched on it a bit. We have an eye-brain system, right? So we whether we like it or not, it's always whatever information we're looking at is always convolved with our eye-brain system. So even if you have a legend beside it, you have to like you might have to fight what your eye-brain system is seeing to really absorb what the legend is saying. So what we should do is work with our eye-brain system, use it to support what we want to say. Can you ask me that question again? Because I think I got off track.
Sure. Well, I guess what it comes down to is I think sometimes you can have trouble convincing academics of the value of integrating art
Oh,
into STEM as like a public outreach thing. So I'm wondering if you, as somebody who obviously has a lot of experience with this, can better explain the value of it to people who might not fully understand the value of using art as an outreach medium.
so first of all, when you want to communicate visually, artists are the ones who've been doing this for centuries. So if you look at their techniques, you've got a whole toolkit for communicating visually and working with the eye-brain system. Has it been hard to convince scientists? Oh boy, back when we started Hubble Heritage, it was continual struggle and battle. But somewhere along the line, without me noticing over time, it flipped. And now everybody's coming to me and saying, please help me communicate this. So, and everybody's excited, very excited about it. It crosses all of the sub-disciplines in astronomy. Everybody from planets through to cosmology wants to know how to communicate better with their figures within their papers and out to the public. So it's also become in 2009, when it was the International Year of Astronomy, we were asked to really, as research astronomers, communicate with the public. And that's been taken to heart. And I think over the years, the young people really took it, the young researchers took it to heart. The young researchers were interested in visual communication, and now they've come all the way through. They're established. And so everybody's much more interested and willing to do it now and spend it's a lot of time to do it. People, I taught a course, I did it first in Zurich and then I taught it at U of M. It's called The Art of Scientific Visualization. It's a really hands-on course and people just love it because it's just projects and exercises like you would do in art college. And they just learn so much. And the one student once told someone, Jan has taught me how to see. And
Oh,
it's just so sweet, eh?
yeah.
I met my goal. I was very happy. But and there was also now the other thing I want to mention is that at the professional research level, I have colleagues, we have a group called Cosmos Canvas, and we are making color Python code for color maps for particular parameters in astronomy, things like the Doppler shift for the velocities, and convincing everybody to use them. So we haven't published a paper because we just keep making new color maps. That's all the fun that we have. But we've got people starting to use our color maps to help communicate in professional venues more clearly. If you're giving a talk, you don't want someone to be reading the legend and then you go off to the next slide and they never even got to look at your plot or your map. So these are for situations like that, especially, so people can see right away, almost at a glance.
Well, well, you heard it here first, folks, how valuable art and science can be when combined, which is a fantastic segue to remind you to go find the Salvador Dali art session that my colleagues Danielle and Don are working on as part of this pack that we've sent you, where you can use the art of Salvador Dali as a way to communicate some space concept to your students. So I want to thank Francis and Jan both for joining us today. This has been a fascinating conversation. I could spend all day on it. I feel like we've only just scratched the surface of all the ways that color and astronomy and space can overlap. Hope everybody is very excited for Space Week. Francis and Jan, have you any plans for Space Week?
I haven't had time to think about it yet. What
No
should I do
problem.
on Space Week?
What should you do for Space Week? Anything. Get out and look at the stars, although I feel like I don't need to encourage you. Any excuse. Francis, what are you planning to do for Space Week?
As I always do, feet on the ground, head in the stars.
And an ethos to live your life by. Thank you so much, guys. And everybody, be sure to check out spaceweek.ie for more videos and resources that are as helpful as these ones. And have a great Space Week. Thank you, folks.
Thanks, Rob. Bye.